Okay. Now that we know what we've done this quick review of sets, let's talk about vectors. So the word space really means set. So why not just say vector set instead of vector space? Because spaces imply some rules apply. There is some ordering, there are some operations you can apply to the elements on the set. So we try to be more specific. And we also want to be careful. There's another word here. I want to use element. Okay, so the word element. In the context of linear algebra, the convention is not to use the word element in a set. The convention is to use the word, the scalar, the scalars of a set. So in linear algebra, an element can be called scalar or point or component. And it's unlikely for you to see elements. So see, these elements are all synonyms for members of a matrix. And of course, a vector is a type of matrix. Okay, so these words are interchangeable. Okay, so we can call this point, or component, element, scalar. Interchangeable. Unfortunately, that's how it is in mathematics. They use different words to refer to the same thing. Furthermore, we don't use curly brackets or curly braces. The convention is to use either parentheses or square brackets. Both are interchangeable. Okay, let me pull up my notes. Ron asks which version of Python, anything version 3 or above. Okay, let me pull up my notes very quickly. Here we go, linear algebra. Okay. So what is a vector space? A vector space actually, no, hold on. I don't want to jump ahead. This is supposed to be vector. So vectors are sets of elements. However, vectors are conventionally referred to as spaces with scalars. Okay. Now, and of course, we use lowercase letters to indicate them. So like so, and they will either come with an arrow over them, like so, or like I said in our first session, they could be bold, like so. Okay. So we call the numbers either scalars or components of the vector. Okay. We also want to talk about a linear span, linear combination, row space, and column space. So we have a linear combination. And then we can do an exercise. Combination. Then we will do linear span. Then the column space. And then the row space. And before we do this, we'll also talk about matrices. So we want to be clear with our terminology. Okay. Now let me come to vector space. Let me actually borrow it from the chapter of this book because I thought I had written it here. A vector space over the field K with the following axioms. Okay. The axioms are vector addition, vector multiplication. So let me pause over here and turn to abstract algebra in a moment. Okay, here we have, it says that a vector space phi over the field. What does over mean and what does field mean? So let's pause here. I'm going to open another document to talk about abstract algebra a little bit. So this will be abstract tutorial 1. Okay, so I say this will take about 15 or so minutes. But I mean, if you do not have exposure to abstract algebra, this is going to take you this will take you very far. Later on, when you, I don't know, want to read more advanced probability theory or go into something called measure theory, knowledge of abstract algebra will be super beneficial. So we'll begin with something called a binary operation. Okay. So this is abstract algebra tutorial. Binary operation. A binary operation is some sort of arithmetic operation that you can apply to the elements of a set. For example, addition and multiplication are both examples of binary operations. Okay, so let's establish this terminology, binary operation. And then we have our first special type of set in abstract algebra, which we call the group. A group can be expressed as a tuple. And again, tuple is a set. Curly. Okay. Now, tuple, 3 elements, we would say a tripole or three tuple or 4 tuple or 5 tuple. So however many elements you have in that set, you'd say number tuple. Okay. G is the set. And here the star indicates the binary operation. So it can be multiplication or addition. If there are some certain rules, we don't use the word, it's quite vague. And these are the axioms that apply to the group. By the way, the group is the foundation we will build on top of. So other types of sets in abstract algebra are variations of groups. We first have something called closure. What does closure mean? Closure means that if you were to perform a binary operation on the elements of the set, the outcome would be another element that also belongs to the set. So let me actually change this to G. Okay. What's an example of such a rule? The integers. If we take 2 integers, or let's keep it simple. If we take the natural numbers, add them together, you will get another natural number. So 5 plus 5 gives you 10, which is still an element within the natural numbers. Multiply them, you will also get another element. But then division doesn't apply, because if you divide, for example, 4 over 5, the result is not going to be division. So that operation does not apply to that set. Okay? So there's closure. Then there's identity. And identity says that there exists a number such that when you multiply it by any of the elements in that set, you get the element again. So here, what number could that be? If we were talking about the integers, what number if we multiply it with any element, it would give us the same number. So for example, let's say a is 5. A times what would give you 5? The number 1. So here I stands for that. And this is a unique element. This is a unique element. Exactly the one. So the identity says that there exists a number such that multiplied by an element of the set, you get the same number. And then there is inverse. Okay, we'll see an example of this. But there's a number. If you have a number and you multiply it by its inverse, you will get that unique identity element. And then there's associativity. Which says that, well, for example, if you're doing multiplication, multiplying b times c and then multiplying it by a will give you the same result if had you done a times b then times c. So it's associative.